Welcome to Microlecture 16 on Lewis acids.
Okay, so by definition, Lewis acids are electron pair donors, and Lewis acids kind of get all the glory. If that's the definition of a Lewis acid, then of course a Lewis base is an electron pair acceptor, but really we only see Lewis acids in the reactions that we're running in the organic chemistry lab. And we see them actually quite frequently. So this, for example, is just a fun reaction that you're not responsible for, but thought I'd share it with you. And there are many, many more where this comes from. So here, AlCl3 is serving as the Lewis acid. And this is just to kind of show you that Lewis acids catalyze a lot of very interesting chemistry. So examples that you might actually see would look something like this. And so we'll start with something you definitely have seen. So HCl plus H2O in equilibrium gives rise to H3O plus hydronium plus chloride ion. And we can definitely label these as acid and base, and so we're going to go ahead and label Lewis acid and Lewis base. Well, this doesn't look any different than anything we've been doing. So the base is the species that has the extra electrons, and so here we see the base serving as a Lewis base by donating a pair of electrons to the acid and giving rise to the products that are shown here. So it helps that we've been using curved arrow notation and we've been doing this all along, so it's pretty intuitive, but we're seeing the acid acting as an electron pair acceptor. Let's look at another example here. So this one will be boron trifluoride, BF3. Boron can only really accommodate 6 electrons around it, so it doesn't have a complete octet because it's such a small atom. And so it's reacting here with an ether. Alright. And so the ether is the base here, and it's going to go ahead and donate its electrons to the incomplete octet of boron. And it's going to result in a Lewis acid-base complex. And here we're seeing how Lewis acid-base definition is a broader umbrella than, say, Bronsted-Lowry, because Bronsted was concerned with protons only. Proton transfers were kind of the definition of acid-base chemistry. And here we're seeing that a proton transfer might not be involved at all. So the resulting Lewis acid-base complex, which involved no proton transfer, has a couple of charges, and it's easy to forget those formal charges. So there's a -1 on boron and a +1 formal charge on the oxygen. But that's the product. And let's look at another classic Lewis acid-base pair. Carbocations can serve as good Lewis acids, and so it's because they can accept an electron pair. So something like chloride has a lot of electrons to give away, and so we can use the electrons on chloride to form a bond to carbon, and we've shown here the formation of another Lewis acid base complex. This time the resulting complex is neutral because we started out with positively charged carbon atom.